In this video, we're going to talk about non-uniform stress, or stress within a rigid body that is not uniform. So the first thing we're going to talk about is we're going to relate internal forces to internal stresses. So first, we're going to start off with some arbitrary rigid body, all right, that we have here. All right, and we're going to make an internal, we're going to make a section cut through the body to reveal an internal surface. All right, so now our rigid body has been cut into a left-hand side and into a right-hand side. So if we just look at the left-hand side of our rigid body, in order for the left-hand side of the rigid body to remain in equilibrium, there has to be some type of pressure or applied force that remains within the rigid body to ensure equilibrium. So these arrows here represent the internal distribution or the internal pressure required for the rigid body to remain in equilibrium. All right, so if we look at a very small fraction of that surface, which I'll label as Q, this area here around point Q, all right, which is the center of the internal surface, we can say that there are going to be three equivalent concentrated force components, which we're going to call them delta Fxx, delta Fxy, and delta Fxz, all right, that they are the concentrated forces that are equivalent to the internal stresses at that point Q, right? So Fxx can be either, it's going to be the normal force, all right? In this case, it'll be the normal force, all right? And it will be either in tension or it'll be in compression. Fxy and Fxz are going to be both shear stresses, all right? So they're going to go tangent to the internal surface, okay? So typically we're going to use this double index notation throughout this book. So what we'll say is, we can say is, like, if we have delta Fij, the first index I will refer to the direction that is normal to the plane or to the internal surface. All right, so in this case, the x-axis is normal to the plane. All right, and then we have the second index is going to be the direction of the applied force or stress. All right, so for Fxx, the direction of the force is along the x-axis. For delta Fxy, it's along the y-axis, and for Fxz, it's along the z-axis. Okay. All right. So using these equivalent concentrated forces, we can define the average stress over that surface element, or over point Q. So if we do that, we can say that our average stress at point Q would be equal to, so our average stress sigma xx bar would be equal to delta Fxs divided by the area. And we can define our area, our differential area, as being equal to delta y times delta z. All right, so this is our differential element This is at Q. All right. So using calculus, we can say that as our element becomes our area becomes very small, that that this fraction here, the sigma xx is going to be equal to the differential of dfxx divided by dA, right? And then we can solve for the total force along the element fxx by using the stresses along the area within that area of around point Q. All right. So how this would look visually is our internal stresses would be distributed along point Q. All right, and this would be our sigma xx. And if we summed up all of those forces, all those stresses, we would get a single concentrated force Fx. All right. In a very similar fashion, we could do the same thing for our shear stresses. All right, we can define tau xy and tau xz using those differential terms as well. And if we rearrange those and integrate them, we can solve directly for our concentrated forces Fxy and Fxz at point Q. So what these look like visually is at point Q, or at point Q for tau xy, this would be our stress tau xy across the whole area around point Q. And then if we integrate it across the whole area, you would get our fxy, right? And we can repeat the same process for tau xz, where we would have all of our pressure going to the left from along the plane. All right, and then if we integrate, so that would be our tau xz, and then if we integrated that, all those forces across the area, we end up with our concentrated force Fxc. So what this was to show is how you could relate external forces to internal stresses. In our next video, we're going to talk about the stress element, which is going to be how we can define stress at any point within a rigid body. And we'll talk about how you can relate stress and strain at during the last part of the lecture.